So here, the thing that I'm going to talk about would be covering a part of a statistical model. So statistical methods assume that the normal data follow some statistical models. So the idea is to learn a generative model fitting the given data set, and then identify the object in low probability region of the model. And then you can say those are outlier. And the effectiveness of the statistical model highly depends on the assumption of the distribution. So it means before doing anything, then you should have some prior assumption about your data. And that's why we have here we'll try to cover two way of doing that. Would be parametric one and non-parametric one. And parametric method assume that the normal data objects are generated by a parametric distribution with some parameter. And in non-parametric one, we just try to model the normal data using the actual data itself. So it won't have that much like a prior assumption. And that's why non-parametric methods often make fewer assumptions about the data, and that's why they are more applicable in more scenarios. Here we'll try to cover some methods that they're using that. Like for parametric one, we'll just try to fit a standard deviation. We'll talk about like maybe a GMM, and for non-parametric one, we'll talk about like a histogram-based outlier score, which is just based on if you can compute a histogram of your data, then you should be able to use it as a way that you can find maybe outlier. So what is a standard deviation? So in a statistic, if a data distribution is approximately normal, then we can say about 68% of the data will lie within one standard deviation of the mean. To be able to compute the standard deviation, you have to compute the mean or average. And once you have the average, a standard deviation would be just the average of the squared of the difference of all the values to the mean and to the average. And by computing that, you should be able to compute the standard deviation. And then, as I said, in math or in statistic, they're saying that if your data is normal, and then 68% of the data will be within one standard deviation from the mean. And the thing is, 95% of that data will lie within a 2 standard deviation, and about 99.7 will lie within the 3 standard deviation. So, and then maybe you can just use that simple technique to say that, okay, I can just use average and the standard deviation, and from that moment I can say, okay, for me, anomaly is any data point that is more than maybe 3 times the standard deviation. Based on new and standard deviation, you can compute the z-score as well, and you can use all those techniques to say that if your data is a univariate, then you can just use this simple standard deviation technique to say that something is off about my data, and whatever I'm seeing is not normal. So then the thing is, then just by fitting the Gaussian or just finding the average and the standard deviation, you should be able to find anomaly, which will be finding something that is not normal or is rare or something that is different. So using that technique, you should be able to find that global anomaly that I mentioned, a number which is not similar to the rest of the number. But the main drawback for the parametric model here is that in many cases, that data distribution may not be known. It might not be exactly normal, and the other thing is, and it can have maybe, let's say, too big cluster it can if you have 2B cluster, but two cluster, the assumption about normal distribution would work well. If you have like a 2B cluster of the data, then you won't be able to just fit a normal and say that what's not here, but what's not in there is anomaly. So in that case, then you should assume that the normal data object are generated by maybe multiple normal distribution, and for every object O here, or for any object which is outlier, the calculation of the likelihood will be based on a mixture of this Gaussian method. So if you can say that okay, the data is like a multimodal, look like multimodal, then you need maybe a mixture of those Gaussian models. But the idea here is if you know and if you have some assumption about your data, just by applying a Gaussian model or fitting a Gaussian model, just by learning some let's say standard deviation of the data, you should be able to say that something is not normal, and then you should be able to detect lots of anomaly and outlier. This would be the first thing that we'll apply on lots of data to see what can we do with these simple models, like how many outlier can be detected using just GMM, which is like a famous model, a simple model. And the other thing that you can just use, which would be super visual like that, would be just a simple model like Boxplot, which Boxplot is like a standard way of displaying the distribution of the data, and it will be just based on 5 number, which is minimum, first quartile, median, third quartile, and the maximum. And the minimum and maximum is a function of IQR, which is like a interquartile range, which means distance between the first quartile and the third one. So just using like this box plot, you might be able to say that, okay, if something is out of my range, if something is like super off from the data, then maybe that sample is not normal anymore, and maybe is fraud, or maybe is different. So and if you wanted to be able to map it to what will be the relation between these two, you can say that if that data was like a normal as well, then it should be somehow identical to finding all those number which will be more than 3 times the standard deviation of the data. So the thing I'm saying right now is like there are lots of basic or simple model that you can just use, and then you should be able to catch lots of global anomaly that they are super different from the rest of the data. And here the assumption is like if you have like a univariate data like that, you should be able to capture anomaly easily. The other technique that here we're going to cover is histogram-based outlier detection, HBOS, which assume the features are independent and calculate the degree of anomaly by building histogram. So the basic idea is for each feature of dataset, a histogram is created, and then for each instance in dataset, the inverse height of that bin will computed, and then if you have multiple feature, then you will multiply those number together, and then you should be able to compute a score for your anomaly. So it's basically the inverse of the height of that bin multiplied together for your different features, and then you will have your score. This is one of the non-parametric models because you're not assuming any distribution of your data. You're just making a histogram of your features. The thing is, because here you're assuming that the data, all those features are independent from each other, it will be a lot faster than all those multivariate approach, but for a cost, and the cost will be the precision would be lower here, because you're assuming, because you're treating each feature independently, you're making a histogram of it, and then you're multiplying them together. And using that technique, they just said that if you look at the paper, they will say that they kind of managed to find those global outlier similar to the other technique, but for the local one, they were not that much good. So, and the other drawback is here, whenever you have a feature, sometimes you have to kind of find a bin, like for the age or for cost, you're making lots of bin, and then you're making that histogram. So that's one of the, I would say, even famous and old technique that you can just use to be able to tell what's normal, what's not, just based on the histogram of the data. So the first one was like parametric one. This one was like non-parametric one. These are just basically like a statistical models that you can use, and we'll test them in the workshop, during the workshop as well. So we can say, you can see what is the difference, and like what is the performance of this technique in different data set. But the other technique that I want to talk about here in this session would be those distance-based anomaly detection. So here the assumption is like a data point that is like a far distance from the nearest neighbor is regarded as a outlier. So if you have a point which is far from all those, far from the rest of the data, or far from the k nearest neighbor, maybe that one is outlier. So there's two techniques, not more than two techniques. The two famous one will be just a k-NaN, and the other one is local outlier factor, LOF. That I'm going to talk about them briefly here, and then we'll try to use them during the workshop as well. So k-NaN is a simple non-parametric lazy learning technique used to classify data based on similarity instance in a distance metrics, such as Euclidean, or it can be like Hamming distance, Manhattan distance, or any kind of metric that you want. So here, to be able to use k-NaN for that, the first thing that you have to do is you have to, for every record that you want to see that if it's for every record in your data, you have to find the k nearest neighbors. And then you can say anomaly score is a distance to here. You can use two different ways of saying that. It can be, if once you have that k nearest items or point or sample, you can pick the further, like the case one, the one which is like a further from it, or you can just use the average distance to all those k nearest neighbor. And then you can say the anomaly score is maybe the average distance to that k nearest neighbor. And then you can have a threshold that say that, okay, if the distance to my k nearest neighbor is super high, then maybe that point is anomaly because it's far from all those k neighbor. And that's why k-NaN is like a global anomaly detection, because given all the data, it will just look at one of the sample. We'll try to see that if that sample is far from all of its neighbor, and then based on the cutoff or threshold, we'll say that's anomaly. And for sure, one of the maybe drawback is, what is k? Like how should you set k? And is 10, 20, 50 is enough? And how can you measure the performance of it? So that's why finding k would be super hard for k-NaN, because then here you have a parameter which is k that you have to maybe guess based on the complexity of your data, and the second parameter kind of would be that threshold that you have to use, and by changing that threshold, you will have different kind of anomaly, so an outlier. So these are maybe the thing that you can play with to kind of have like a then you can kind of say that how many maybe outlier you're expecting in your data, and you can change or tune k and that threshold to be able to find it. So this will give you a global anomaly. The other technique is local outlier factor, or LOF. So the LOF method scores each data point by computing the ratio of the average of density of the neighbors, the density of all those neighbors. So it just so it's like the k-nearest. So to be able to do that, for sure you have to find all the k-nearest neighbor, and then you will compute the local density for a record, for that record or sample, using what they call like LRD, which is like a local reachability density, which is basically an inverse of average of distance to the k nearest neighbor. So for the k nearest neighbor method, we're computing this, as I said, like an average distance to the k nearest neighbors. Here they have like a concept which is LRD, which is the inverse of it, and that's like a local density for each sample in your data. And then they are computing LOF, which is local outlier factor, which is computed by comparing the LRD of a record of the sample with the LRD of its neighbor. So the local outlier factor is the average of the ratio of the local reachability density of outlier with his neighbor, with his k neighbor. And as you can see, the lower is the LRD, so the higher will be if the density of your point is lower and the density of your neighbor's node is higher, then maybe that node is anomaly. So it's not just based on so the reason that I say is like a local outlier detection, because it's not just computing the distance by its own. It's just comparing that to its neighbor as well. So it is like, that's why it's like based on the ratio of your density with all the neighbors density as well. So that's why you can say that that LF value of less than 1 is an indicator that that observation is outlier, and if it's greater than 1, maybe that's maybe it is like outlier. So using that number or the ratio of density, they're trying to say that what is anomaly, what is not. So this is like the second technique that is based on the distance of all the points in your data. So here I just want to say that it was kind of like a wrap up of some of the statistical and distance-based models that you can use to be able to find anomaly in your data. These are maybe one of those simple, easy to use models, understandable and interpretable models that you can just use to find fraud, and then say why these are fraud, what's the reason for it, and even though they are simple, usually they are effective as well, because if you have any kind of anomaly or outlier that is far from the rest of the data, which was the definition of anomaly, these simple techniques should be able to catch it. So as I said, for the first session, I tried to kind of give you some overview of what is outlier, what is like an anomaly, and what are the simple way that you can handle it. We will try to have we'll have different data set as well. Like we will come up with some synthetic data. We'll use MNIST or some other image data. We'll even we can have ImageNet as well. So then we can have one of the class as anomaly or few of the class as anomaly, removing them from the trained data, and then train a model based on the remaining classes. And then we'll try to see that if those class that we put aside, if the model will be able to detect them as anomaly or not. We'll use a credit card fraud data set, and we'll use some time series data set, and the KDD COP 99, which is like a famous intrusion detection data set as well. We'll try different data set, and then, so we'll get familiar with them. We'll try a supervised model for them as well. So then we can compare and see what's the difference between the actual the score that you can get using a supervised one versus all the other techniques that you will see during the workshop. For the first session, we'll play with this data. We will apply some statistical model on top of them, like finding the, as I said, like applying a GMM, or making all the histogram around them, or applying the KNN and all other distance-based methods to see that what's different. And the reason that I'm trying to have different kind of data set is like to be able to say that which of these model is better for which kind of data set. Because like sometimes, as I said, you have a global anomaly. Sometimes you have a contextual anomaly. And that one will be a bit harder for some of the models to be able to say this is fraud or not. And so we'll try to play with different data set, and then we'll try different models in each session to be able to learn how we can tackle this problem, and how we can detect all this fraud in different type of data set. So that will be the end of my first session, which will be the overview of anomaly detection and what is outlier and how can we find them. The first session will be mostly an overview, and then we will get to know each other. We'll learn what we want to know more about this problem. And so for the second one, as I said, we'll try to cover different machine learning technique like isolation forest, 1SVM, clustering, all these methods. And based on the feedback that I will get in the first session, we'll try to even tune the workshop in a way that we'll try our best to learn more from each other as well. So that will be the end of the session for this one.